We've been working on this for a while, so in some sense this is an update, but I'm not going to assume everybody knows the past on this. So I'm going to spend a little time on the history of this before going into developments and things like, what we've done since then. So this is essentially the outline. So the question is, why did we do this? And this is a somewhat tongue-in-cheek representation of the history of this. For a long time, astronomy's had a standard format, and that was a very positive thing. On the other hand, it's getting quite old in the tooth, and has caused us a number of problems in particular. And so we felt we had to do something about that. So a little bit about the details of the FITS format. As I said, it dates to about 1980, and you have to understand the era that it was developed in was the punch card era, and you still see reflections of that time period in the format. It has, your keywords are limited to 8 characters. The metadata is essentially put on 80 character cards. So it's a pretty simple way of putting the data in a file. The thing that, we had problems with not having easy hierarchical format, but the thing that really got us was one of the things that's very important to us is being able to map a pixel coordinate to the sky, a sky coordinate, or in the case of spectrographs, a wavelength and sky coordinates. And there is a convention, there's a standard for FITS for dealing with that, but it's not very flexible. And for HST, we're not even talking about subsequent telescopes, we have found that we require very high precision in that mapping. People see systematic effects down to 5/1000ths of a pixel, and this is over thousands of pixels. And we need that accuracy, so we need to be able to describe that transformation to high accuracy. But doing that requires a pretty complicated transformation system, one that the FITS didn't handle. We have to deal with running these things, running these files through pipelines, and over time, it just trying to shoehorn the things that we need into the FITS format just got more and more difficult and burdensome. There have been attempts to try and modernize the format, but they really haven't gone anywhere. And again, there are people who have tried to work around these limitations by extensions, but for example, handling hierarchical formats is pretty kludgy. You gotta layer this on the 80 character card thing, and before you know it, it looks pretty awful. So we went looking for something better, and we didn't find it. And I won't go into the details of what I thought the shortcomings were of various well-known formats. That's in the paper. We didn't do this, because we, coming up with a new format because we thought it'd be a cool thing to do. We knew we'd encounter a lot of resistance to, coming up with a new format. We did this so we could stop banging our heads against the wall. That's really our motivation. I would generalize, the problem for our finding a solution, pre-existing solution, by generalizing this way. Most of the science formats that exist are done by people who deal with data, and they're very familiar with handling large data arrays. That's where their focus is. Their focus is on efficiency, but they're not particularly, I would say at one point, it's not true anymore, but to me, astronomers knew only one data structure, and that was an array. And, other things were suspicious, not needed, too complicated. And so they generally came up with too simplistic solutions of dealing with metadata. On the other hand, there were people that did, very, very interesting and complex things with metadata, but they didn't care about binary data. They neglected that. And it seemed to us that, it should be possible to merge the strengths of both of these. And that's the approach that we took. So I'll talk a little bit about the desired qualities. I'm not going to go through each one of these in detail. I'll highlight a few of these. Having an archival format was particularly important in astronomy. I mean, you have to consider that, every so often you find something interesting that changed in the sky, and you want to know what it looked like before. And so being able to go back and see previous observations of the same thing is extremely useful for understanding the history of it. And this all started, we have photographic plates that go back over 100 years. So there's been a long history of building archives of observations. And so there's certain characteristics of being archival. That is, it should be something you could use for a long time. You should be able to figure it out without complicated specifications and things like that. So that's a particularly important thing in astronomy. And I imagine there are other fields that could be important as well. I will say another thing that was really important was that it be easily extendable. For example, with FITS, you had to go through the standards body to get anything changed. And that eventually became essentially impossible. It's difficult, I think it's a big mistake to think that you can anticipate all the future kinds of structures, things that you need in a data format, and make a standard around that. I think you have to allow for some mechanism for extensibility. And extensibility not just in a global sense, but being able to extend for a domain. Maybe it's in geology or some other field. You have particular needs in that field that nobody else needs. Astronomy is the same way. You would, and maybe even more specific needs. An institution has its own specific needs, an observatory, an instrument. And so it's really important to be able to allow each one to come up with extensions that are easily publicized and easily used without having to go through a lot of hoops. And I'm talking about more than just conventions of how to do things. I'll mention that a bit later. Schemas and validation, we do a lot of this in an operational sense. That's important to us. A lot of times people tell the developers that you'll never get a file that will do this. As an example that I recall, we were told we would never get files with 0 exposure time. Don't worry about it. We eventually got files with 0 exposure time, and that causes a pipeline to crash, and it takes a while to figure out what actually went wrong. So a little bit of an odd thing here is, this may be, again, mostly for astronomers, I don't know. A lot of them, especially when they're dealing with spectra, things that don't have a huge amount of data, sometimes like something in a simple to use format. They don't want to use your library. They don't want to use your software. They have their own software. They might customize it. And, so a list of text for a spectrum, a table, they just may want something that they can read in another way. And that is, there's a long history of that in astronomy. And so it'd be nice to be able to support that. If somebody wanted, instead of seeing stuff in binary, that they want to print smaller data sets in text. That's why that's there. This last thing was not part of our original sort of requirements, but when we started working on it, we began to realize this typing information was really important. And I'll expand on that a little bit in the next slide. In any case, there was nothing about these kind of requirements that seemed very specific to astronomy. You know, this ought to be usable in many fields, and that was our attitude, was to try and enable that. So I'm not going to go into great detail on this. You can see this in the documentation, but the whole idea behind this is that we combine the two by putting metadata, information about the structure of the file, all in YAML. And that is because there are lots of tools that we can use in YAML to deal with the metadata that we don't have to deal with ourselves in writing new libraries of code. So where a data set is in this structure and the metadata is described in, is in the YAML. It is followed by, it could be followed by no binary blocks, but it could be followed by any number of binary blocks. Typically, an array would correspond to one binary block, but there are other possibilities. I'll talk about chunking, in which case, an array may consist of many blocks that are chunks. But that's the basic idea. But there's more to it than that. I'm going to go a little bit out of order. So we use JSON schema to define schemas for files and use those for validation. We use YAML anchors to avoid copying large pieces of information, arrays that might be shared amongst data sets or combinations of things, so that you only have one copy of this and then the other things refer to it and actually share exactly the same item. And now I'm coming to this typing issue. We use the YAML tags, and we use them very extensively now for typing information. And the tags are basically a signal that what follows, within that structure should be interpreted a certain way. It could be a tag for an array, a tag for a table, or that this is a unit or a quantity, coordinate system, all sorts of things for which you say, this means something and it should be handled specially. And in the Python library that we have, this information is used to turn that stuff in YAML into a specific Python object. And very often this has been done by convention. If you see this attribute, then you should interpret the contents of this attribute a certain way. This is more flexible. You could, the units could be used anywhere. There's no implicit convention. You can say, I have a new quantity, an attribute of something I made up, and I use this tag, and that says you should turn that into a quantity. Currently we use the AstroPy library, which handles units. These quantities can be, you could do arithmetic with them, like in NumPy, that handles conversions automatically, things like that. So this is a really key feature for us. And finally, we want this to be language neutral. For example, you could put objects into a file using Pickle, but now you're tied to Python. And in an archival sense, that's not good. You want something where you can interpret the contents independent of a version of a language or something. So it was extremely important to separate the two. So I'm going to list some of the uses that are planned or currently. I imagine many people have heard of the James Webb Space Telescope. There have been recent news on this, so I'll take a little entertainment interlude here to show a few pictures. I can't help myself. Figured it was very timely. Some of the things that have just been released. Basically, one way you can tell whether it's a star or galaxy, if you see these diffraction spikes, it's usually a star. And if you don't, it's usually a galaxy. Here's a dust nebula. Anyway, back to the main program. As you may have heard in this morning's talk, there's upcoming telescope that's being worked on now, that's basically a survey-like telescope. It's a very wide field of view. Whereas James Webb Telescope will handle both FITS and ASDF in the pipelines. Though I should say, even the FITS files have embedded ASDF content in them. None of them are pure FITS anymore. To simplify the software and pipeline thing, the Roman telescope will only support ASDF. The DKIS telescope is using it in its pipeline. There's a ground-based telescope called the Rubin telescope, which is intended to do massive surveying of the sky, doing the whole night sky every three nights. It's that fast at covering the sky and has a big field of view. Is using that for world coordinate system interchange. And then there's some other uses, some not in astronomy. It has picked up some non-astronomical uses. I'm not going to spend much time on this one, since you can see this in the paper that will be coming out. I mean, the main point is, in using this for Webb, we have learned lessons. We've figured out, we should change things. So this first part is making it very explicit. It's not an astronomy format anymore. We want this to be very generic, and so we're moving name references to space telescope, and the location of the repository. All the rest are details I'm not going to really go into here. The Python package that we use to support this, we've made it easier to make new extensions. So we've changed the system to do that. We've also made it easier to deal with configuration issues. We've added a few things to make it easier to understand the structure of the file. And the next slide will show a little bit of this item and the next item. One of the things we can do, for example, is, given an ASDF file with tags, we can extract information from the schema that's associated with that tag and print information in info to show this. And so we have some extra stuff to deal with more flexible compressors. You probably can't read the details of this, but what you're going to see here is it shows the nested structure of items. When they exist, it'll show that it's a reference to something else, a copy, not a copy, that is, it's referencing. And the comments you see after, so it shows you the type of the item, whether it's an object or a primitive type, the value if it's a primitive type. We've actually implemented a mechanism that allows you to, if you're converting in an object, to expose the internals of that object too, which we'll be doing to some of these things. Finally, the comments you see after that are extracted from the title in the schema. And we'll be adding more things, like if you add a very detailed description, maybe you want to document exactly how this value is computed, or what it means exactly. It takes half a page of information. You put that in the schema. We'll have a mechanism for extracting that too. That's not done yet. So anyway, that's an indication, make it easy to introspect. We have search capabilities that do something similar. So I'm going to go on to talk a little bit about what improvements we have planned. We're very, this is to support Roman, by the way. We need to deal with being able to large data sets. Roman will have very big data sets, and it will be running on the cloud. So we need to add features that make chunking support, which we plan to use ZAR for, and cloud optimized storage options that make cloud usage efficient. We would like to make it more integrated to existing visualization tools, and as a storage option for other projects. For example, being able to put a pandas data frame in there, or SciPy or something like that. That we're just beginning to think about. It would be nice for astronomers to be able to see schemas in a way that's a little bit easier to understand than looking at the original schema format. And ultimately, we're not really serious about it being language neutral unless we do an independent implementation, but that will take some work. So I'm going to spend the rest of the time highlighting one of the things that would not be considered metadata, but is important to us. I made reference to this as the World Coordinate System information. What we can do with this format is serialize complicated functional models into the ASDF file. Now, people would look at this and think, that's not really what I thought metadata would look like. But this information is crucial for understanding the data. I mean, if you don't know where a pixel lands on the sky or what wavelength it is, you don't really understand it. And we found it's important to bundle this information with the file in a flexible way. So in this I'm going to sort of go through this quickly, but what you're going to see is that, I'm going to construct a very simple compound model. And the thing I'll highlight here is you're going to see two Gaussians being defined with different parameters. Some of these parameters have units in them. Then there's a power law, and you see at the bottom here that there's a model that's the sum of these three. And just for illustration, I plot what that particular model looks like. And so what we want is to be able to save that model in an ASDF file. And we can do that now. This is just a code to illustrate that we create an ASDF model with only this as the model as a content under an attribute called model. We write it to a file, read it back in, and you'll see that that model that is read in is not identical. It's not the same ID of the model that we wrote out, but it evaluates exactly the same way. I mean, it's a replication of the original model. The contents of the file, I don't want to spend a lot of time on this, just to give you a flavor of, this is the kind of thing you'll see in the YAML. You see some of the transform says add, and it adds the things in the list before. The thing forward says this is the forward transform. We support inverses. You see the various parameters are specify that the following value is a quantity, and then it lists the unit. You see the tags are being used here to indicate, how these values, quantities should be interpreted by the software. Bounding boxes, things like that. So, and that model is basically represented in text, like as you see here, and that's how it gets saved. And it can be, in principle, either could, if you wanted to read it and figure out what was going on, you could do that. You could read it in Python and get a functional model out of it that way. So it's very explicit in that sense. So at this point, I will stop and just abdicate for its use, and if not in a native way, as a data format, as an interchange tool between organizations or domains or things like that. And I see the 3 dots there tell me I should end the metadata of this talk. So if you have any questions, please, thank you for your time, and please ask them.
Sorry, where's the mic?
Oh, here it is.
Okay. Okay. Thanks very much, Perry, for that excellent talk. And we do have a few questions, so we'll go ahead and just read those off. You'll be patient with me for a second. Okay, so, right, we have one from Mohammed. Do the binary blocks of a given type have a fixed endianness or a specified schema or structure? For example, like Apache Arrow or MSGPAC. And has the use case of streaming data been considered so you can read and process both data and metadata as it's coming in?
To the second, yes. At least in the sense of, you have one item that you can stream to at a time. I mean, we don't have a multiplexing scheme or anything like that. As to the first, actually, the structure of the binary blocks for arrays, looking at them arrays, I mean, they could be anything, right, with extensions. But for arrays, we allow for endianness. We allow new arrays to be views into an existing array, so that you can have an array defined here, and then in the metadata, another array which is a view into that array. So you have the strides and the offsets and all that kind of stuff. So all the machinery that NumPy supports is pretty much embedded in the metadata part. So that's where all that information is in the YAML tells you how to interpret that binary block. There are a couple of compression schemes that are embedded into the header of that binary block, whether it's compressed with this or that compression. But otherwise, everything else is in the YAML.
Okay. All right, I think we have time for maybe one or two more. Martin asks, could you please give an example of a non-astronomical use, and why do you think they might choose ASDF?
I'm not sure I'm the most qualified person to answer that question, but it just seems to me transparently generic. I mean, if you need nested data sets or associated, so example of in astronomy, we often, so you have the actual image, but you also have an error array that goes with it, or multiple error arrays, a data quality mask, things like that, and you may have multiple sets of these. So the grouping is transparent. You have an item that says, this is this detector, and you can have all those arrays clearly associated with that detector. You could have a different detector in the same file and have a set there, and not rely on conventions that say, if it says this name, then it's this detector, that this belongs to that, all that sort of thing. So, yeah. Okay. So, go ahead. Yeah, I don't want to take too long.
Yeah, no. And then we'll have time for just one final question. Michael asks if you can briefly compare and contrast with, for example, HDF5, or sorry, just HDF and NetCDF.
I don't know if I can do that briefly, but I mean, the things I'd like to highlight there is this is much more transparent in that HDF5 is a very complex specification. So seeing the metadata is not easy to extract in any simple way. A second thing is HDF5 does not have a very efficient dictionary kind of mechanism. They go by groups and stuff, but that's not very optimized for, we find that dictionaries are very, very powerful tools, and I think it's a little weak in that area. So I'll leave it to those two things.
All right, thanks so much, and let's thank our speaker again.